Okay, so we start with from our previous discussion. Okay, so we're discussing the covariant form of Maxwell's equation. Okay, we're discussing the covariant form of Maxwell's equation. Okay, so remember what we did in the last class. Okay, so we started with this Maxwell's equation, and our aim was to write in relativistic covariant form. Okay, note that these Maxwell, there is nothing wrong in writing in this form. Okay, they are relativistic. So if these equations are valid in one frame, then they are valid in any other frame. Okay, but they are not manifestly covariant. Okay, they are written in terms of curls and vectors, three vectors. Okay, divergence, etc. Okay, so we want to write it in a manifestly covariant form. Okay, that's why we're doing this exercise. Okay, so consider first inhomogeneous equations, del dot E equal to rho and del cross B equal to this. Okay, and then we showed that these equations gives me in terms of F mu nu, this is a field strength tensor. This inhomogeneous Maxwell equation become this. Okay, where J nu now is a 4 current vector. Okay, J mu is equal to 4 current vector. Okay, this is your charge density. Okay, with multiplication of C. So rho is charge density, C rho is J0. Okay. So these are the inhomogeneous Maxwell's equations or Maxwell's equations containing source term. Okay. Now what happens to this other two equations, then namely del dot B equal to 0 and del cross E equal to -1 over C del B by del T. Okay. This we showed that these equations is nothing but the statement about the statement about the identity. Okay, and that identity is this. Okay, so in terms of field strength tensor, okay, this inhomogeneous Maxwell's equation, sorry, homogeneous Maxwell's equation, okay, reduced to del mu F nu rho plus cyclic combination of this. Okay, del nu F rho mu plus del rho F mu nu equal to 0. And remember how we derived this? It is because, so if you go back, okay, so we defined in between, we defined a 4-dimensional Levi-Civita tensor or symbol in 4 dimensions. Okay, right? One can actually do a little better. Okay, one can consider this. Let us consider this quantity epsilon mu nu rho sigma. Okay, del nu f rho sigma. Okay, we considered this quantity and we showed that in the components form. So see, we considered this quantity actually, right? Yeah, we consider this quantity. And then we show that for mu equal to 0, it reduces to whatever we obtained before, okay, namely this. Okay, and for mu equal to I, any special index, okay, it reduces to this. Okay, just I think I removed one this thing. Okay, in between there was something in between. I erase that. Okay. So at the end, we have epsilon mu nu rho sigma f nu f rho del nu f rho sigma equal to 0. Okay. So let us start with, let us see what is this. Okay. You can immediately argue that by using the expression for f rho sigma del nu. So if I substitute the expression for f rho sigma, what is the expression for f rho sigma? Del rho a sigma minus del sigma a rho. Okay. So I am not going to put 0 here. I have to show that. Okay. So you see that this thing is epsilon mu nu rho sigma del nu del rho a sigma minus del sigma del nu del sigma a rho. But you see, this is symmetric. Del nu del rho is del rho del nu. This is symmetric, but this is antisymmetric in nu rho. So this term goes out. And again, del nu, so there is this thing is it. Del nu del sigma. This is also symmetric in nu sigma, but this is antisymmetric in nu sigma. If you interchange nu sigma, you will get minus sign. Okay. So this is also 0. Okay. So that means epsilon mu nu rho sigma del nu f rho sigma equal to 0. Okay. Note that this mu rho sigma are summed indices and this is free index. Okay. So I can keep this index as it is and I can cyclically permute nu rho sigma, which gives me cyclic permutation of this. And if this is equal to 0, then that cyclic permutation of this object is 0. Okay. So I will get, if I do that, I will get del nu f rho sigma plus del rho f sigma nu plus del sigma f nu rho equal to 0. And this is what we got. So this is a very simple and elegant way of doing it. Okay. So your homogeneous Maxwell equation is nothing but the statement about the identity. It's nothing but the identity, and that is expected because your homogeneous Maxwell equation, namely del dot b equal to 0 and del cross e equal to minus 1 or c del v by del t, they actually provide a redefinition of electric and magnetic fields in terms of potential. They give us nothing, no new information. Okay, namely that E equal to minus grad phi minus 1 over c del A by del t is a solution for del cross E equal to minus 1 over c del V by del t, always, for any A and any phi. Okay, so as expected, we got the identity. So this is the identity, and it has a name. It's called Jacobi identity. Okay, it's general. It's not invented by Jacobi, but it's still called Jacobi identity. Sometimes it's called gauge identity also. It plays an important role, very quite important. Okay, fine. So now we have a field strength tensor. So what we have now? So we have the field strength tensor defined. Tensor f mu nu equal to del mu a nu minus del mu a mu. Okay, and one can write the Maxwell's equation in the covariant form, okay, which are del mu f mu nu equal to j nu by c, okay, and and that identity. Okay, del mu. So I will write this thing, shorthand notation. So this bracket indicates that it is a cyclic permutation. Okay, so these two equations encodes in a beautiful manner for all the Maxwell's equations. Okay, but remember now my F mu nu is given in terms of this vector potential A mu. And we also know what are electric and magnetic fields. Okay, E is equal to EI, ith component of electric field is Fi0, and Pi is equal to Pi. Let me see what is this Pi. So my Bi is minus half epsilon I jk s jk. Okay, so if when I solve this equation, okay, I get the solution in terms of solution for A mu. Okay, once I get the solution for A mu, I can plug it here, and I get the electric and magnetic. Okay, given this current density, given this current, one can solve this equation in principle. It's very difficult task to solve this equation, but in principle one can solve. After solving, what we'll get? We'll get vector potential. Okay, then I will use these relations and I will get the form of electric and magnetic. That's it. Okay, and as you can see, these equations are written in a covariant manner, manifestly covariant manner. These are the tensor equation. Okay, here, any questions so far? Any question? So now, okay, if there are no questions, so let me proceed. Okay. Now one can discuss the transformation of E and B, electric and magnetic, under Laurent transformation. So, how this electric and magnetic field changes if I go from one frame to another. Note that as it stands, these electric and magnetic fields are not written in terms of 4 vectors. They are still usual three vectors. Okay, but we know that how under Laurent transformation, Laurent transformation say lambda, okay, your F mu nu, okay, goes to F prime mu nu, which is equal to this tensor of rank 0 2. Okay, so it will be lambda mu alpha, lambda mu beta, F alpha beta. Okay, so you have frame X, then you have frame X prime. This is combined notation. X0, X1, X2, X3, X0 prime, X1 prime, X2 prime, X3 prime, and so on. Okay, so I'm looking at the Laurent transformation. Okay. Okay. So I will use this relation. I will use this relation. Okay, fine. And let me restrict to. Okay? So let me restrict to Lorentz transformation. Okay, let lambda be a boost along positive x-axis, or in this notation x1 axis. Okay, so if the lambda is the Lorentz transformation which is a boost along positive x1 axis, okay, that means two frames, okay, are moving related to each other. Okay, all the axes are coincides, and this x prime axis is moving related to x axis. That's it. x1 and x1 prime. Okay, with velocity say v. Okay. Then in that case, we know what is this lambda. Okay. Remember, lambda is a matrix. Okay. So what is this lambda in that case? You tell me. What is the Lorentz transformation written in the matrix form? When it represents a boost along x-axis. Okay. So first will be gamma. Okay. Then minus gamma beta, minus gamma beta, and gamma. Okay. And rest, this will be 0, 0, 0, 0, 0, 0. Then this will be 1 because y goes to y. And this will be 1 because z goes to z. So this is my particular Lorentz transformation. Okay. This is not most general Lorentz transformation. These are some particular Lorentz transformation. And under this, I want to discuss the transformation of electric and magnetic field. So now let us use that previous relation, this relation. So, and let us focus on this component f prime I0. Okay. So mu equal to I, mu equal to 0. So what it will be? This will be lambda I alpha, lambda 0 beta, f alpha beta. Agree? Okay. So let us sum it. Okay. So this is equal to lambda I. Let us say alpha equal to 0, beta equal to 0. But alpha equal to 0, beta equal to 0, f0, 0, that is 0. So either alpha is 0 and beta is j, or alpha is j, beta is 0. Okay. Two things can happen. So let us consider alpha 0 and beta j. Okay. So this will be f0 j. Sum over j is implied. Okay. Plus lambda ij, lambda 0, 0, f j0, plus alpha can be any special index and beta can be any other special index. Okay. So lambda ij, lambda 0 k, f j k. So we have exhausted all the possibilities. Okay. Remember, there is a sum of j and k. So this is equal to, so now I can use the antisymmetry of f. Okay. So it will be lambda I0, lambda 0 j, minus lambda ij, lambda 0, 0, f 0 j, plus lambda ij, lambda 0 k, f j k. Okay. Right. Now you substitute. Now you use, this is at this step it's quite general. Now you use here this given Lorentz transformation. This given Lorentz transformation says that lambda 1, lambda 0, 0 is equal to gamma is equal to lambda 1, 1. Correct? Then lambda 0, 1 equal to lambda 1, 0. Okay, equal to minus gamma beta. Okay, and rest of the entries are 0 except is lambda 2 2 and lambda 3 3. But you will see that this will not come into the picture. Okay, clear? Okay, so let us use that. Okay. So let us fix now I. I is your floating index. So let us fix now I. Okay. So let us suppose that I want to calculate f prime 1 0. So this is equal to lambda 1 0 lambda 0 j. Okay, so I will use now directly. Okay. So here it will be lambda 1 0. What is lambda 1 0? 1 0 is minus gamma beta. And remember, the gamma is 1 over square root of 1 minus v square upon c square, and beta is equal to v by c. Minus gamma beta, I equal to 1 minus gamma beta, and j is summed over. What this j can be? I equal to 1. Okay. See, 0, j cannot be 0 because it is a special index. Okay. So j can be 1 or 2 or 3. But you see, 0 1. Okay, 0 1 is this quantity. 0 2, 0th row, second column. Okay, this is 0. 0 3, that is also 0. Okay, so this will survive only when j equal to 1. Right. So I have minus gamma beta coming from this. Okay. Then I have so let me write it. Okay. Better to write. So it will be lambda 1 0, then lambda 0 1 minus lambda I am fixing to be 1. Then if I is 1, okay, look at this. Okay, if upper index is 1, then lower index can be 1 or 0, nothing else. Okay, so it will be 1. So j, but j cannot be 0. So j has to be 1, lambda 0 0. Okay, so here it will be, so this will be equal to f 0 1. Clear? Plus I j k sum. Okay, so my I is 1, so f lambda 1, j has to be 1. Okay, lambda 0, so f 1. If f is 1, j can be 2, j can be 3, j can be 1, or j can be 2 or 3. Okay, but lambda 0 2 and lambda 0 3 are 0, so this sum will give me 0. Okay, so I will have only this. So this will be equal to, okay, so this will be equal to lambda 1 0 lambda 0 1. Lambda 1 0 is minus gamma beta. Lambda 0 1, lambda 0 1 is also minus gamma beta, so it will be plus gamma square beta square. Okay, minus lambda 1 1 lambda 0 0, lambda 1 1 lambda 0 is gamma square. So this will be equal to n into f 0. Okay. Fine. So this is equal to gamma square. Okay. So gamma square into beta square minus 1. Okay. F 0 1. Okay. But beta square minus 1 is minus of gamma 1 or minus of 1 or gamma square. But then I will write here 1 0. So it will be 1 0. So this implies that but f prime 1 0 is nothing but your E prime 1, x component of electric field, transformed electric field, and your f 1 0 is E1. Okay, so E1 prime is equal to E1. So there is no change in the longitudinal component of electric field. That means if the boosts are along x-axis, then the electric field along x-axis is not going to change. Okay, fine. Now let us consider another component. Okay, so f prime 2 0, f prime 2 0, f prime 2 0. So this will be gamma 2 0, gamma 0 j. Let me write it first. It will be gamma 2 0, gamma 0 j, 0 j minus gamma ij, so gamma 2j, gamma 2j, gamma 0 0, f 0 j, so f 0 j, f 0 j, okay, plus lambda 2j, lambda 0k, f jk, lambda 2j, lambda 0k, f jk. That's it. Okay, fine. So let us see. Lambda 20, lambda 20, lambda second row, okay, and 0th column. Okay, so it is 0, 1, 2, 3, 0, 1, 2, 3. Okay, so second row and 0th column, that entry is 0. Okay, so lambda 20 is 0. Okay, lambda 2j. Okay, now you see this is non-zero. J cannot take 0 value, 0 index. Okay, so J is spatial index. In that spatial index, lambda 2. Okay, second row. In the second row, I have non-zero entry only when the column index is 2. Okay, so J has to be 2 here. So I will get F02. So this will be equal to minus lambda 2 2, lambda 0 0, F02. There is a summation over J, but now that summation has gone and I retain only index 2. Plus lambda 2, same argument holds here. Okay, lambda 2, J has to be 2. If J has to be 2, then K has to be 3 or 1. Okay, so there is index here. So this is equal to lambda 2 2 is 1, lambda 0 0 is gamma. So this is minus. So I will write it as gamma F20. Okay, there I use the antecedent. Plus gamma 2 2 is 1, gamma 0. Now if K is 3, then gamma 0 3 is 0. Okay, if K is 1, then gamma 0 1 is non-zero. So it will be gamma 2 2, that is 1, lambda 0 1, F2 1. Okay, so it will be gamma F20 is 2 plus gamma 0 1. Gamma 0 1 is minus gamma beta. It will be minus gamma beta. Okay, and F21. Okay, F21 I can write it as minus of F12. So this will be equal to gamma E2 minus plus gamma beta F12. But F12 is what? Okay, F12, if you use convention, okay, so I need to express F in terms of B. That is required. So just tell me, yesterday I think I gave you the formula, how to convert, how to express, how to write F in terms of B and B in terms of F. So can you just tell me the formula?
Sir, I think it is minus BZ.
Pardon? No, no, no,
F1
no.
to
You tell me the. You tell me in terms of epsilon. What is Fij? I gave you that formula, right? Minus epsilon. I think Ijk. Just see in the notes. Just see. It will be dk. Something like this. Okay. I gave you this formula, right? Just see. Just check in the notes. Okay. So
Yes, sir.
F12 equal to epsilon 1, 2, 3 B3. So it is BZ. Okay. So it is minus BZ. So this is equal to gamma E2 minus gamma beta BZ. Okay. So B3. Okay. So this is equal to gamma into bracket E2 minus beta. Beta is V by VB3 by. Okay. So that is your E prime 2. So you see now the electric field along y direction is now changing. Okay. So in the frame which is moving along x-axis with velocity v related to a frame unprimed frame, the electric field looks like this. So it is subtracted from your original field by this quantity, by this much amount. Okay. Is that clear? Okay. Your transformed electric field is now subtracted from your original field. It is the subtracted field in the sense that you have to subtract something from your original field. Okay, and then you have to multiply by gamma. Similarly, you can show that that E prime 3 is equal to gamma E3 minus, plus this time V by C P2. Okay, so you have now the transformation of electric field E1 prime, E prime 1 equal to E1, E prime 2 equal to gamma E2 minus beta B3, and E prime 3 equal to gamma E3 plus beta B2. This is not the way your four vector special component of four vector should transform, right? This is not the way your special component of four vector would transform, right? Okay. So this is the difference. Your electric and magnetic field, they are not the part of any four vector. Like your velocity v, 3 velocity, is not the part of four vector. You should understand that. Okay, 3 velocity v is transformed in a completely different manner. We have seen that it's transformed in a complicated. It is v prime equal to v plus u v ux something divided by something was it, some messy expression. Okay, so this is not the way your special component of four vector would transform. Okay. Yeah. Now let us consider Fij. F prime Ij. F prime Ij will be lambda I alpha lambda j beta F alpha beta. So let us say that I want to evaluate X component of magnetic field. Okay, so that means I have to put here, you can anticipate that you need to put I equal to 2 and j equal to 3. Then I will get B1. So f prime 2 3. Let us suppose I want to calculate. Okay, so this will be equal to lambda equal to 2 alpha lambda equal to 3 beta f alpha beta is equal to. Now if lambda upper index is 2, then alpha has to be 2. There is no other choice. Okay, because lambda 2 0 is 0, lambda 2 1 is 0, lambda 2 3 is 0. So lambda 2 2 lambda 3 3 f alpha f 2 3. But these two are 1 1, so this will be f 2 3. It's easiest of all. Okay, so but beta 1 is equal to minus half epsilon 1 2 3 f 2 3. Okay, so this implies that b prime 1 equal to b1. That's it. So magnetic field along x direction is not going to change. Okay, so I will write. You can take this as an exercise. Okay, show that b2 prime b prime 2 equal to gamma b2 plus beta E3, okay, electric field, and b prime 3 equal to gamma b3 minus beta E2. So you see that the magnetic field and electric field has no separate existence now. See, the argument is the following. There is no frame which we should prefer over another frame. All frames are at the same status. Okay, so you should not make any statement which is privileged to a particular frame. Okay, so in the special relativity, one should not make any statement which is giving privilege to a particular frame. Okay, there. So we have several frames, okay, related to each other by inertial transformation, by Laurent transformation. These all are inertial frames. All are related to each other by Laurent transformation. One should not prefer one frame over another. One can do computation in one frame, okay, but when you conclude something, when you want to make a rule, okay, that rule is such that it should not make any distinction between these two frames, between all these frames. Okay. Now, suppose in a given frame, if someone tells you that there is an electric field, okay. Suppose in a given frame, suppose someone tells you that there is an electric field only. That statement is not consistent with special relativity, because one can go to any other frame and say that no, there is an electric field as well as magnetic, which are given by this. Now I know the transformation. This, and these three. So if someone gives you this, and this, okay, and b equal to 0, okay, what is going to happen? If b equal to 0 in one frame, okay, what is going to happen? This electric fields will transform like this, okay, with b equal to 0, okay. So E1 prime remain E1, E2 prime will be shortened by factor gamma, okay, or maybe increase whatever that it will be scaled by factor gamma, and similarly this third component of electric field also scaled by factor gamma. But now you see in the transform frame, your b's are zeros, okay, So your x component of your transform field is 0, magnetic field. But the second component will pick up something through this. Although your B is 0, your primed B prime 2 and B prime 3, they are not 0. So in general, I have a magnetic field in that frame. Okay? So one should, special, the moment you go into the high relativistic regime, one should not talk about electric field and magnetic field separate. Okay? There is no existence at all. So there is no this electrostatic, magnetostatic has, there is no meaning to it. So in fact, one should start studying electrostatic and magnetostatic from this point of view. You first consider special relativity, then consider this transformation, and then now you take the non-relativistic limit, or whatever you want to do. Now you specialize your cases. In fact, this is how the Landau and Lipschitz proceed for electrostatic. Okay. So in general, when you take into account special relativistic effects, there is no separate existence for electric and magnetic. Is this fact clear? So when you say electrostatic, this is a wrong statement. It is not a Lorentz covariant statement. Okay. Fine. Similarly for magnetostatic. So we should really talk as electrodynamics. That's it. There is no electrostatic or magnetostatic in the when you take into account special relativistic effects. Okay. So you have now, you know how electric and magnetic field transform under this particular Lorentz transformation. This, my Lorentz transformation is fixed. Okay, this is my Lorentz. Now your job is, now take the exercise, find the transformation of, transformation is not a correct word actually, find the transformed field electric and magnetic field, transformed electric and magnetic field. That means this for general velocity boost. Okay, so your Lorentz transformation is general velocity boost. It's not a velocity, the relative velocity is not along x-axis or not along y-axis or not along z-axis. You have a boost along any arbitrary direction. Okay, so I gave you again, I know what exercise I gave you. Okay, so I gave you this exercise to show. Please do that. Okay, then only then you should be able to do this. Okay? So in the exam, the question will not be like find this. This question is will not appear like this. It will be like find, consider lambda along x-axis, find lambda. Okay, for boost along x-axis. Generalize to arbitrary boost. Okay, this will be A. This will be B. Use this relation to find something. Either it will be electric field or maybe another thing which we discussed before. Okay, something like this. Okay, so this will be a question. So if you know this, you can try for this. Then from this you can try for this. Okay, so it will be a step-by-step question. Okay. So derive this expression. Get this expression. Okay. Another exercise you can do is that first thing, express vector r in spherical polar coordinates. Consider vector in spherical polar coordinates. Okay. Then you determine how Laurent transformation looks when spatial coordinates are spherical polar coordinates. Okay. So we are using T, X, Y, Z, right? Okay. Now you use this, okay, and express this T, R, theta, phi. I can do that. Okay. I can express any three vectors in terms of X, Y, Z or R, theta, phi. Speak, say. Okay. Now you write down the Lorentz transformation. Suppose there is a boost along X-axis. Take that boost and see how in these coordinates, now I have from this transformation from T, R, theta, phi to T prime, R prime, theta prime, phi prime, right? Okay. There will be a matrix connecting these coordinates. Do you agree? Okay. Find that matrix. Okay. So this is equal to lambda. Okay. Find lambda. Okay. Use that lambda. Okay. Use lambda to write transformation. Use that lambda and consider, use lambda and consider a frame in which E is given by Q over R square, R cap, okay, and B is 0. Okay. Find E prime and B prime in spherical coordinate. Okay. I want to see how this 1 over R square, how this behavior changes when you transform. Okay. Is this question clear? So try this. Try this. There are lots of exercises. Okay. Unless you do this, you will not get any feeling about the Lorentz transformation. This is your usual point charge. I have an electric field of point charge. And now I'm transformed, and now I'm going into a frame in which is moving related to first frame with velocity v, which is along x-axis. Okay, right? You find that. You just, if you know this, you know this. Remember, these coordinates does not care about this transformation. Okay, does not care about whether your spatial coordinates are x, y, z or r, theta. Any coordinate, right? Any three independent coordinates. It does not matter whether you work in spherical polar or in Cartesian coordinates. Is that clear? You can approach this problem, said problem, in another way also, in simpler way. Okay? I gave this because I want to find this lambda. I want you to do this exercise. How this spatial vector changes in polar coordinates. Okay, one can approach this problem in a by using this exercise, you find these transformed fields. You know Ex, Ey, Ez. Okay? You know E prime X, E prime Y, E prime Z. Okay? Correct? So from the beginning, given to you is that E is R cap, something times R cap. Okay? You find out X, Y, Z components, use those X, Y, Z components, okay, and transform them in the frame which is moving related to x-axis, along x-axis with velocity v. Okay, don't use this general velocity boost. Okay. Then you find Ex prime, Ey prime, Ez prime, and again reconvert it into spherical polar coordinate. That is another way. Okay. But this way you know now. The calculation will be hard, but this you know for sure how to do. Express this E in Cartesian coordinates and use the Laurent transformation to get E prime, Ex prime, Ey prime, Z prime. Then re-express this into polar coordinates. Okay? Is it clear? Any question?
Any question?
No, sir.
Sir.
Hello?
Hello. Yes, sir. Means in this example that you showed that from if E is given in spherical polar coordinates, we convert it to Cartesian, then we do the transformation.
Just a wait for a second, wait for a minute. Okay, my audio is creating problem. Just wait for a minute. Okay, tell me.
Sir, we are converting from spherical polar coordinate to Cartesian, then doing the transformation, and then again converting to T prime, R prime, theta prime, phi prime in spherical polar coordinates. So my question is that is it then possible to directly go from spherical polar coordinate in one frame to the spherical polar coordinate in the...
That is what I gave you. This is that question.
Okay, okay, I got
question.
Okay.
Okay.
Okay, okay, okay.
You solve this, then you solve this also. Now since you have asked me question, you solve this and then you solve this also, and check the consistency.
Okay, sir. Okay, sir.
Is this clear? Okay.
Yes, sir.
Unless you do these kind of things, you will not understand. Okay. All these indices and tensors and everything is fine, but ultimately you have to do some useful calculation. Okay. Any question? Okay. So the important thing, takeaway lesson is that there is no separate existence for electric and magnetic field. There is no in special, as far as special relativity is concerned. Okay. And we know that special relativity is the true picture of nature at high velocities. Okay. That's why one should not talk about electrostatic, magnetostatic, and so on. Okay, when you are in the high velocity regime. Okay. Clear? Good. Okay. So now we have now we know the dynamics of relativistic point particle, dynamics of relativistic point particle in electromagnetic field. Okay, we also know how to write electromagnetic field in a covariant way. We also know how to express the equation which governs the dynamics of electromagnetic field. What are those equations? Those are Maxwell's equations. How to write those Maxwell's equations in a covariant way, that also we know. We know how to transform electric and magnetic field. Okay, this much we know. Okay, but only one thing is pending, that is I have not told you. Okay, see here the Maxwell's equations represents dynamics of electromagnetic field. Okay, so now see, try to understand the logic. To represent the dynamics of relativistic point particle, we started from action. We first constructed the action. Okay, and then by using Euler-Lagrange equation of motion, we arrived at the equation of motion for relativistic free particle. Same strategy we used for relativistic point particle coupled to electromagnetic field. That means the relativistic charged relativistic point particle interacting with electromagnetic field, external electromagnetic field. Now we are talking about the dynamics of electromagnetic field. So the electromagnetic fields are no more external now. There is a dynamics, okay, which is happening in that electromagnetic field. Okay, so electromagnetic fields are changing. They are not external now. Okay, so the question is, can I construct action or Lagrangian for electromagnetic field? Okay, but before that, let me write this electromagnetic the Maxwell's equations. Okay, del mu f mu nu equal to j nu by c in a slightly different form. Okay, so let me I will write this in terms of where the appearance of vector potential is explicit. Okay, so it's very simple thing to do. So del mu, I will use the explicit form for f mu nu, del mu a nu minus del nu a mu equal to j nu by c. Okay, so del mu, look at the first term, del mu a nu minus del mu a mu, right? Because I can, this del mu is same as del nu, okay, equal to j nu by c. Okay, so this I already told you that this object is called D'Alembertian box a nu, okay, minus del nu, and this will be your 4 divergence that I will write like this. Okay, 4 divergence. This is your 4 divergence. Okay, so if you are in, you can always write this del mu a mu kind of thing equal to j nu by c. So this is the equation. So I just converted this equation. This is same equation. Okay, so this is the equation of motion for a mu. Okay, and a mu is a function of space and time. Okay. So given this 4 current, in principle I should be able to solve this differential equation. Now the question is how to get this equation from starting from the action. That is one question. Okay. How to construct action for electromagnetic field, or in other words, action for electromagnetic field, or you say Maxwell theory. Maxwell's theory. Maxwell's theory, I mean the theory of electromagnetic field. That is first question. And secondly, you see there is your secondly, you see the way I define F mu nu. F mu nu is del mu a nu minus del nu a nu. And I said that given a mu, I can calculate this second rank tensor, and hence I know electric and magnetic field. Okay, clear? But you see, if I transform this a mu, if I transform this a mu in a following way, if I transform this a mu by this a mu plus del mu of some scalar function, say scalar function, what should I say? Scalar function, say lambda. Okay, this is not Laurent transformation. This is scalar function, or I think I should use something else. Some scalar function, say S, but S I use for action. Okay, this is a problem. Okay. So some scalar function, say F. Okay, there are no indices. So F is scalar function. Okay, so F depends on X and T. So I consider this transformation a mu goes to a mu plus del mu F. So this is my new a mu. This is not the Laurent transformation. This is something else. Okay. What happens to F mu nu? You see, F mu nu goes to what? Del mu a nu. If a mu goes like this, then for a nu I should use a nu plus del mu F, right? Okay. Here, sorry, del mu F minus del nu a mu. A mu goes to a mu plus del mu F. So this is equal to del mu a nu, okay, plus del nu F minus del nu a mu minus del mu F. This term cancels with this, and again I recover my same field strength tensor. What does it mean? It means that I can change my potentials in this way, where F is any arbitrary scalar function. Okay. So I can change my A like this by keeping my electric and magnetic field same. If F remains same, then electric and magnetic fields are same, because ultimately F is the one which tells us about electric and magnetic field. Okay, it's not the potential but the electric and magnetic field which matters, right? So my electric and magnetic fields are same, but my potentials are now changing. and they are if I change in this particular manner, then I observe that electric and magnetic fields are same. Is this fact clear? Okay. This transformation is called what is known as gauge transformation. And it plays most important role in our study. Okay. In quantum electrodynamics, or even in Dirac equation coupled to electromagnetic field and so on. This is the backbone of your theory of electrodynamics. Okay. So these gauge transformations, okay, what are these gauge transformations? Gauge transformations are the one which are given by this, which changes the potential by gradient. This is called four gradient, four-dimensional gradient. Like this, okay, you define the gradient. If I change the potentials by four gradient, then my electric and magnetic fields are unchanged. They remain unchanged. Okay. So this point and this point, these two are, I will not discuss them in detail right now. Ultimately, I will discuss it, okay, when it requires. Okay. But keep in mind that we have to finish this story. Story is half yet. Okay. One has to construct the action principle for electromagnetic field or Maxwell theory, and one has to address the issue related to gauge transformation. I will tell you something here itself. Okay, by using the gauge transformation, one can remove this term. Okay, what this basically tells you, it tells you that if I change A by this much amount, my electric and magnetic fields are unchanged. That means this is the freedom which I have in choosing my A. Okay, I can choose my given some A mu. Suppose if you give me some A mu, for which say del mu A mu is not 0. Okay. I can have a 4 vector for which del mu mu is not 0. You agree? Okay. Why I'm taking del mu mu? Because this is appearing in this term del mu mu. Okay. So now I can construct a new vector potential denoted by A prime, okay, such that del mu A prime mu equal to 0. Can I do that by using this? Yes, I can choose this F in such a way that this new A prime mu satisfy this. What do I mean by that? Then del mu, for that, what I need? Okay, del mu, I will substitute the, for A prime mu, I will substitute this. So it will be del mu A mu plus del mu F. Okay, this I demand to be 0. Okay, that means I have del mu F equal to minus of del mu A mu. But this is, you said that this is non-zero, so this will be some function. I can solve this equation. Okay, so this is a box F equal to minus something, some function. I can solve this differential equation and I can determine F. So for that F, if I use that F here, then my new A mu is guaranteed to have 0 divergence. If I have 0 divergence, then I will substitute here. I will get box A nu equal to J nu by C. Okay. And now if I specialize the case for which there are no sources. Okay, so I have empty space. There is no charge density, there is no current, free current. Okay. Yeah. Okay. Then this term will go away. So this is 0. So this is what? This represents now the wave equation for describing the dynamics of each component of vector potential, this 4 vector potential. Okay. So when I have, what is your wave equation? So equation of this sort. The wave equation. Now what I have instead of f, I have del 2 del 0 square minus gradient square. There is factor of c and everything will be there. Acting on a0 is 0. Similarly, acting on a1 is 0. Similarly, a2 is 0 and a3 is 0. Okay. So I have 4 wave equations. Okay. Clear? And which one can solve. It's very easy to solve. You know how to solve wave equations given the boundary conditions and so on. Okay, but now you see the problem. The problem is that I will just highlight the problem. Okay, see, you will get the 4 oscillatory functions, right? So you have the, you know the solutions for these. Solutions will be e to the power I omega t minus kx kind of thing. Okay. For each of these. Okay. Clear? Hmm? So I have 4 functions which each of them represents a plane wave. Each of which represents a plane wave. Okay, so there will be some amplitude factor here for each of them. At the end, what you will get? You will have 4 direction of polarizations now, right? Because you have 4 oscillatory functions. So 4 direction of polarization, but electromagnetic field has only 2 direction of polarization, namely transverse direction. So if the electromagnetic wave propagates along z direction, then you have the propagation along this and this only. How to reconcile with this fact? How to reconcile this with this known thing? Okay, so the answer is, again you go back to this and you study in a proper detail these gauge transformations. Okay, so the gauge transformation again put further restriction, okay, on 2 of these 4. Okay, so actually 2 of these 4 are not dynamical again. Okay, and only 2 of them are dynamical, and their oscillation gives me 2 direction of polarizations. That's it. That will end the story in terms of age. You can get this result if you use your usual Maxwell equation, del cross your vector Maxwell equation in terms of E and B. Okay, but in terms of age, how to get this? How to get the 2 direction of polarizations? Okay, for that you need to study in detail the gauge transformations. Okay, but this I will postpone, okay, to some other time. Okay, to some another time. So I will not discuss this right now. This issue and this. Okay. Clear? So now our study of electromagnetic field relatives in a coherent way is finished. It's finished in the sense that whatever will be required in our relativistic quantum mechanics is now finished. Still, these points are there. There are other points also. Okay. Okay. So why I did this study is why did this electromagnetic field first is that this is the your first physical realization of field, concept of field. Electromagnetic field is, you know, from the beginning, you know, from your 12th standard or BSc, your electromagnetic field. So this is the first realization of the concept of field, which we are going to discuss in detail. Okay. Secondly, it is the place where you must consider the special relativity. Maxwell's equations are not Galilean invariant, Galilean covariant. They are Lorentz covariant. So we must take into account the special relativity. Okay. In the process, it allows you to digest the tensor algebra and all these mathematical techniques required in future in known setup. Okay. So now you are, I hope that you are comfortable with the tensors, dealing with the differentiation of tensor, 4-vector, transformation of 4 vectors, and so on. Okay, right? But the story is not complete. It's just a half story. It's not finished. Okay. After that, I will change the course, okay, and I will consider now, is there any other wave equation one can construct apart from this equation governing the electromagnetic field? Can I construct any other wave equation which is relativistically covariant? The answer is yes. Okay. See, these electromagnetic fields, there is no rest frame for photon, or there is no rest frame for electromagnetic field. Okay. So if I try to give some meaning of particle to this field, okay, for example, photon, okay, those photon will always move with speed of light. There is no rest frame for photon. That means I cannot use this thing to represent the particle moving with velocity less than c. For example, electron, high energetic electrons, or high energetic, say for example, any nuclear particle inside the nucleus. I cannot use this. First of all, these will represent the massless particle. The mass of photon will be 0. Okay, rest mass. When I say mass of photon, is always mass of something. I always mean rest mass. Okay? There is no rest mass for photon, simply because there is no rest frame for photon. So I cannot use this to describe the quantum mechanics of massive relativistic particle. Okay? So I need to use something else. So you have in quantum 1 and in quantum 2, okay, you have studied, you started your quantum mechanics by the Schrodinger equation. Okay, fine. And you, for a given Hamiltonian, you solve this psi. It represents the quantized particle interacting with some potential, or the particle, the quantum particle in some potential. It could be free, or it could be coupled to harmonic oscillator, or in hydrogen atom, and so on. Okay. Yeah. But that particle will have some mass. I cannot now use this theory obviously, okay, to describe the quantum mechanics of such a particle. So firstly, I need to, the problem with this equation, one has to understand one has to understand the problem with this equation itself. When I take into account special relativity, okay, then one should understand, one should give the escape route. That means one should construct an analogous equation of this. What is the relativistic version of this? Okay, fine. So this is what we are going to do now. Now we will construct the relativistic versions of this. Okay, fine. But before going into this, okay, let me tell you the problem associated with this equation. Okay, so now actually we are discussing the relativistic quantum mechanics. Okay, so I think I should pause for a minute, and if there are any questions, I will answer, because now we will go to relativistic quantum mechanics. Till now we were discussing classical physics, relativistic classical physics. Any questions so far? Hmm? Are you getting everything?
Yes, sir, fairly.
Fairly. Okay, and no trouble whatsoever. Pace is fine.
Yes, sir.
Yes, sir.
Okay. So you see that we have learned the contravariant vectors and covariant vectors. Okay. And there we observed, or we saw, that the quantity like this transform like under Laurent transformation. This quantity transform like covector. Okay. This quantity transform like contravariant vector. Okay, but this quantity transform like scalar. Okay, fine. You're comfortable with this now, this notation and this. Okay, so how this quantity will transform del x0? This will transform like zeroth component of 4 vector, right? How this quantity will transform? This quantity will transform like spatial components of 4 vector. And what is that 4 vector? That 4 vector is this. Okay, agree? So if I want, suppose my equation contains 2 time derivatives and 1 space derivative. Okay, suppose my LHS of, suppose I have some equation whose LHS contains 2 time derivatives and 1 space derivative. Okay, will it transform is there any chance for this equation to transform like a scalar, or this term? In LHS, there is a term which contains two time derivative and one space derivative, suppose. Okay, is there any chance for this term to transform like a scalar? If you understand, then you will answer this question.
No, sir.
No. Okay. Can you tell me such a term which I can construct? So I can have A del T square plus B del xi, right? Agree? Okay. Similarly, suppose if I have a term which contains one time derivative and two space derivatives. Okay, two space derivatives, I will write that as del xi del xj. Okay, then I may have del xi and del. So let me write in a shorthand notation because it will be convenient. Suppose I have something like this, del I. Okay, something like this. This is what we can get. Okay, there will be a term where it's not divergence, but it will be something like this. Okay, so you adjust some indices here, and there will be a term like your Laplacian. Okay, so this term, okay, obviously will transform like it will not transform like a scalar, right? Okay. This term, there is a because of this term there is a chance that sorry, okay, this term will transform like a scalar, okay? At least under rotation, because del I. Okay, so let me write it in a form. I'm talking so many terms I'm throwing. So let me write this term in a proper manner. So suppose I have a term like B gradient plus C gradient square. Okay. So I have one time derivative and at most two space derivatives. Is there any chance for this term to be Lorentz invariant? Lorentz invariant, I am saying. That means if I go to other frame, this term will remain as it is. Is there any chance? If I consider this term, A del 2 by del t square plus B gradient square plus C, yeah, that's it, only this much. Now tell me, is there any chance for this term to be Lorentz invariant? And similarly tell me, is there any chance for this term to be Lorentz invariant? This term you told me that is not Lorentz invariant. What about this term and what about this term?
Sir, the one on the right, there is a chance that it can be a Lorentz invariant.
It can be, there is a chance that it can be a Lorentz invariant. Okay.
Yes.
Why? Because there are two. See, you can fix, suppose A equal to minus B. Okay. Then this you can write as del T or del 0 square minus gradient square. And this is nothing but your del mu del, which is Laurent scalar. Okay. So this term transform like a scalar. Okay. This term may transform like a Laurent scalar for this choice of A and B. But suppose if I drop that restriction and I demand that I want to construct a term which are Lorentz covariant, in the sense that I'm allowing the term to be a 4 vector, or I am allowing the term to be 4 tensor, or I am allowing to be term to be higher rank tensor. But it should be a tensor. It should be an appropriate tensorial quantity. Okay. Then can you tell me which two terms can survive? Which two terms can give me that kind of restriction? Will this represent that equation? Will this represent that equation? This you told me. This is Lorentz invariant. So this is actually a scalar. Okay. But scalar also is a tensor of rank 0, 0. Okay. So I will count this also. So you have answered this. What about this? Or I will give you new term. Suppose if I give you this term. Suppose if I construct A times del del x0 plus B times del del xi. Suppose if I construct, if I have term like this, say A equal to, is it Lorentz covariant?
Yes, sir.
It can be Lorentz covariant, right?
Yes, sir.
Okay. So I can construct equation out of it. Some equation say 0. So I will act on this quantity. I will act on some function. I can equate it to 0. I can form an equation out of it. Okay. What about this term? Suppose if I construct term like this, A times del del x0 plus this plus B times this. Will it transform in a covariant way? Covariant, not necessarily invariant, covariant. Covariant means that if I have a term like A, say if I give some index, it must transform like lambda mu nu A nu.
It will not transform, sir.
It will not transform because this will transform like a zeroth component of vector, but there will be a problem here. Agree? Is it clear? Okay. There will be a problem here. Okay. This will not transform as a spatial component, this whole thing, entire thing. Okay, spatial component of 4 vector. Okay. So this, as a result, this will not be Lorentz covariant. Okay. That means if I have equation like this, okay, and if I want to give to it a relativistic status, okay, then we expect some problem to occur, because any statement which one can draw from this equation will be frame dependent. Okay. Clear? So that is the essential problem with your Schrodinger equation. So Schrodinger equation is actually what is your Schrodinger equation? Schrodinger equation is I h cross del t psi equal to minus h cross upon 2m. Schrodinger equation for free particle. Let us suppose that. Let us see if I take that. Then this is nothing but this is the statement about this operator. But as you said before, this entity is not will not transform covariantly. Under Lorentz transformation. So when I say transform, I mean now Lorentz transformations. I mean under Lorentz transformation. So what one need to do? Either one should consider a second order. One should consider an equation involving second order derivative with respect to time, or one should reduce the order spatial derivative. Okay? Either you consider something like this, okay, A plus B, okay, or one consider A agree. There's only two way, or you discard and do nothing. That is the only other way. Discard everything and do nothing. You abandon the study. Okay. These are the only three ways. Okay. So this will follow this way, this or this. Obviously, doing nothing will not give us anything. Okay. Okay. This is the only way to make this expression Lorentz covariant. Yes.
So,
What's the question?
if we add Laplace on psi function, so L squared, so that will give us a scalar, right?
Yes, that will give us a scalar. Yes.
And if we add the time derivative twice on any side, then that will also give us a scalar.
Yes.
Then what is the problem, sir?
So this is this. If I consider this, okay, then I will get a Lorentz invariance. That is a much more beautiful. Okay. So if I can choose A and B in such a way that I can write this as del mu psi equal to 0.
Oh, I'm sorry. If we add time operator just once.
If we add time derivative once, how it will transform? How this quantity transform? Del
okay,
x.
Under Lorentz.
Right.
Under Lorentz.
This will transform like a zeroth component of vector, right?
Yes. Yes.
You agree?
Yes.
So this will transform like zeroth component of vector, but this is not.
So if we had twice time derivative, then it would have been fine.
If you have two time derivative, or that means in brief, one should have equal space and time derivatives. Order. The order of derivative of space and time derivative must be equal.
Yes.
Okay. Yeah,
Yes,
that is it. Okay. Then you then one can construct a dynamical equation. This represents the dynamics of psi, right? This equation gives you, this Schrodinger equation gives you the dynamics of psi.
Yes.
So I now want to construct a covariant equation which gives me a dynamics of psi. Why covariant? Because we want everything to be frame independent. Everything to be consistent with the principle of special relativity or postulates of special relativity. I am not assuming anything extra. Starting from special relativity, we are deriving these results. We are concluding this. You see now, when the special relativity come into the picture, how it changes. Okay, your ordinary thing will not hold. There is a strong constraint now. You cannot put any arbitrary term in between. Okay, every term you put, it should have some meaning. It should have a tensorial nature. Either it should be a scalar or vector or tensor. Okay. So this gives us one equation. This form will give us another equation. Okay. So first we will discuss about this equation. So we will end up with what is known as Klein-Gordon equation. And this gives us celebrated Dirac equation. This is also celebrated, it's not Dirac equation. So this we will do in the next class. From the next class onward, we'll start our study of relativistic quantum mechanics. But before closing this lecture, okay, so let me remark something about these epsilon symbols and give you some exercise. Okay. So we defined. Okay, so this you can think of as aside. Okay. Sometime we need this. Okay. So we define, if you remember, we defined this epsilon mu nu rho sigma equal to +1 for even permutations of 0, 1, 2, 3, -1 for odd permutations of 0, 1, 2, 3, and 0 otherwise. Okay. Now, like the Levi-Civita symbol in 3 dimension, here also we have this product of epsilons. Okay. In general, suppose if I give you expression like this, and now the placement of indices matters. Okay. So suppose if I have epsilon mu nu rho sigma, and I say that I fix the components like this: mu is 0, nu is 1, rho is 2, and sigma is 3. And this is happening in some frame S, in some Lorentz frame S. And now I transform this frame to S prime. How these components are going to transform? That is the question. Or in general, how this epsilon tensor is going to transform under Lorentz transformation. One need to show that it is actually a tensor. How this tensor is going to transform? See, epsilon mu nu rho sigma prime equal to lambda mu alpha, lambda nu beta, lambda rho alpha beta gamma, and lambda sigma say delta. Epsilon alpha beta gamma delta. Okay, this would be the transformation rule if it is a tensor. Okay, so assume for a moment that it is a tensor and see what we get. Whether we get the consistent picture or not. Okay. What is this quantity? Can anyone tell me what is this quantity? Suppose if I now fix mu to be say 0, 1, 2, 3. Can anyone tell me what is this? It will be lambda 0 alpha, lambda 1 beta, lambda 2 gamma, and lambda 3 delta. Epsilon, alpha, beta, gamma, delta. There is a sum over alpha, beta, gamma, delta. How this epsilons is defined? In this way. And I told you before that epsilon is the tensor which takes same component in all frames. Another tensor is your Kronecker delta, which takes same components in all frames. Okay. That's why these epsilons and Kronecker delta they acquire special status. So what is this quantity? Can anyone tell me? Suppose, okay, let me start with this. Suppose if I consider the following, you consider a matrix A, some matrix A. Okay, let us calculate the determinant of A. What is the determinant of A? Do you know this expression? A I1. Okay, so let me put this as A1I, A2J, A. Suppose this is a 3 cross 3 matrix. A3K, epsilon IJK. Do you know this expression? You can see, you can check that this gives me a determinant of A. This is a row expansion of the determinant. This is very simple to check, right? Okay. A1, there is some more IJK. So A, let us fix I to be 1. Okay, and this will be A23, A33 minus, sorry, A2, J say J is 2 and A, suppose J is 2 and K is 3. There is some more IJ. Okay, so 2, 2, A3, 3 minus A2, 3, A3, 2. Correct? Okay. If I sum more Ij, if I fix I equal to 1 and sum more Jk, I will get this. Okay, plus. Okay. There is some more I also. Then I have to consider A1, 2. Okay. So I equal to 2. So I equal to 2 means epsilon 2 jk. Okay, so if I sum over j and k, what I'm going to get? A2 I equal to j, I is 2, so j is 1 and 3. So 2 1 A3 3, okay, minus A2 3 A3 1 plus. Now I is 3, so 1 3. Okay, if I is 3, j is 1, j and k could be 1 and 2. Okay, so 2 1 A3 2 minus A2 2 A3 1. But this is what? This is equal to just your determinant, right? This is A11, A12, A13, A21, A22, A23, A2, A31, A32, A33. So if you take determinant A11 into this minus this, okay, so that is this term. Okay. A22 minus A22, A33 minus A23, A32. That is this term. Then A12, A21, A33 minus A23, A23, A31. Okay. So that you can write as minus of this into this. Okay. So there will be, so if you take this, if you arrange this minus sign here, you will get the determinant. Okay. Fine. So one can write the determinant in this fashion. Okay, but suppose if I keep, so this is what, this is the expansion of determinant in first row. You see, when I expand it in first row, I will get this expression. If I had put 2, 2, 1, 3, okay, then I will get the expansion of determinant in another row, and so on. Okay, but I will be calculating the determinant at the end. So these expressions like this will give us the determinant of these objects, of the matrix formed by these objects. In general, suppose if I have something like this. Okay. So suppose if I have something like this. A, I, K, A, J, L, A, I, J. So A, I, L, A, J, M, A, K, N, epsilon, L, M, N. Okay, this will give me what? This will give me epsilon I, J, K, determinant of A, right? So because this here I fixed this I to be 1, J to be 2, and K to be 3 here. This K is 3 here, this J is 2 here, and this I is 1 here. So actually there is epsilon 1, 2, 3 factor is there, which is 1. Okay, if I have indices here, then I could have written IJK determinant of A. Okay, is this clear? This is just the expansion of determinants. In view of this, what will be this? Now you come here or here. Okay. This will be epsilon prime mu nu rho sigma will be equal to, right? The entire thing will be what? Will be equal to epsilon mu nu rho sigma into determinant of lambda, right? You convince yourself about this calculation first. You try it. You try it home. Okay, try it. Take any determinant and use this expression and see whether you get a correct answer or not. Okay,
sir, for the
right.
second term, in the next page, for the coefficient of A12, Levi-Civita 213 would be would have negative value, right? -1.
Which one? Two. Let me see. So 2 here. So 1 here and 3 here. So 2, 1, 3. 2, 1. This will be negative and this will be correct. This will be negative. This will be positive. So this will in fact correctly match with the usual definition of determinant. Okay. So epsilon prime mu nu rho sigma is equal to determinant of lambda epsilon mu nu rho sigma. What it tells? It tells you that this is indeed a tensor, okay, but with this quantity. Okay. Now this quantity, as we have seen, this quantity is either +1 or -1, right? Determinant of Laurent transformation is either +1 or -1, depending upon whether it is improper or proper. Okay. So I can have either this one or this one. Okay. So these almost transform like a tensor apart from this determinant, or I should say Jacobian. of the transformation. It's really the Jacobian of the transformation. Here we are using Laurent transformation, so that's why I'm using this lambda, and it's a good determinant of lambda. So the quantity like this, which transform like this, are called the quantity. The previous one, which transform like a tensor with the determinant Jacobian factor, is called pseudo tensor. So it's actually this epsilon mu rho sigma is pseudo tensor. It will be clear to you in due course why this name pseudo tensor. Okay, so at this moment you just call it as a pseudo tensor. Okay, it transforms like epsilon prime equal to determinant of lambda epsilon. So you give indices here. Okay. There is a way to express this epsilon mu rho sigma. See, it is totally antisymmetric symbol. Or sometime I will say it is a tensor by dropping this name. Okay. When it's required, I will pronounce the pseudo. Okay. There's a way to write this, since it is a totally antisymmetric tensor. Okay. One can write this in a following way. Okay. So you can write this as not this one. Okay. Sorry. The product of two epsilon. Suppose if I take the product of two epsilon, epsilon mu rho sigma and epsilon alpha beta gamma delta. There is no index which is repeating, so there is no sum. Okay. So there is a way to write this product. It's the most general product of two epsilons. Okay. This is determinant of epsilon mu alpha. You keep this mu fixed in first row. Mu beta, mu gamma, and delta mu delta. Then you consider next index, mu alpha, delta nu beta, delta nu gamma, and delta nu delta. Then you consider rho, delta rho alpha, delta rho beta, delta rho gamma, and delta rho delta. Okay, the delta here. And then delta sigma alpha, delta sigma beta, delta sigma gamma, and delta sigma delta. This delta is index. This is Kronecker delta. Okay. So this determinant will represent this product. Okay. And now you can take the contraction. Now you can, with this established, one can consider quantity like this. Epsilon mu rho sigma, epsilon mu beta gamma delta. Alpha and mu are contracted. So alpha, in place of alpha, I will put mu and sum over mu. Okay, there is a summation of mu. Okay. So this you can show. Okay. So one can show from this. Okay. So it's like this will be, so I will put here minus sign, by the way. Okay. Then only then it will match with if you calculate this quantity component wise by explicitly substituting the values of mu nu rho sigma and alpha beta gamma delta. Okay, then you need to put minus sign here. Okay. So this quantity will be minus of this determinant. Okay, this quantity will come here. Minus of this. This determinant of this. Okay. Then one can also show that epsilon mu nu rho sigma and epsilon alpha beta rho sigma is basically minus 2 times delta mu alpha delta nu beta minus delta mu beta delta nu alpha. This one can show. And the third one is epsilon mu rho sigma epsilon alpha nu rho sigma is so you contract beta with nu, so you will get 4 here. Okay. Nu, so it is 4. Okay. And here nu delta nu alpha, so it is delta mu alpha. So 4 minus 1 3 3 6, so it will be minus 6 times delta mu alpha. And if you contract everything, all index, then it will be epsilon mu nu rho sigma epsilon mu nu rho sigma. So this will be minus 24. Okay. So these results, okay, one can this is coming from what? This is coming from antisymmetry of it should be antisymmetric in mu nu, all this mu nu rho sigma. That's it. Then there is no other way than to write in the determinant. You use the property of determinant that if you alter any 2 columns or any 2 rows, you get a minus sign. From that you derive this. It's very simple to visualize. Okay. Now here I am contracting one index. Okay. So nu rho sigma alpha beta alpha gamma delta. Okay. So this itself is a 3. One can write with the same logic. One can write as 3 cross 3 determinant. Now from this you expand this, you get the answer, and then you contract 2 indices. Here one index is contracted. You contract now 2 indices. You will get this result. You contract 3 indices, you get this, and you contract all the indices, you will get a scalar. See, this is a scalar, right? Okay. No index is remaining. This is a scalar. And in fact, this quantity will be true scalar. Okay. We said that this is pseudo tensor. Okay. This quantity will be true tensor of rank 1, 1, and this quantity will be true scalar or true tensor of rank 0, 0. Okay. So this was just aside. This will sometime be helpful. Okay. This will be helpful in our calculation in future. It's given in Jackson and Landau lectures. Okay. Yes, there was a question. Someone is asking something. No question. I think no question. Okay. So we'll stop here, and from next class onward, we will start the relativistic wave equations. Okay. And we'll start our study of advanced relativistic quantum mechanics. Okay. So I will tell you the timings of next class. Okay. So 19th is CSI, right? 19th is CSI exam.
Yes, sir.
Yes,
Yes, sir.
Okay, so you don't want class on 18th. That means tomorrow we don't want, right? So neither MNP2 nor AQM. I assume that. Okay. So can we take the class on 19th after your exam?
Sir, actually the exam is from 3 to 6.
Pardon? Exam is on?
Exam is from 3 to 6.
Oh, 3 to 6. Achha, achha. So there is no way to take the exam. Take the class. Okay, so we'll meet on 20. Okay, then on 20th we'll take classes. Okay, I will tell you the timing. And CSR exam will end on 19th itself, right?
Yes, sir.
Yes, yes, sir.
I heard that it is some the exam for some student it will be on 19th, for some student it will be on 23rd. It's not like that, right?
Sir, it's on 3 dates, but for
Physics
us,
students, I think yes. For physics, it is on 19th.
So all physics students, the exam will be on 19th.
Yes, sir. As far as we know, yes, sir.
Okay, okay. So we'll meet on 19th. Okay. Right. And the MMP2 Professor Durganandani want to take the lecture on 20th. Okay, so I will post on MMP2. So one of you should respond to that message. Okay, I will post on MMP2 group. Like suggest the time. Okay, and that time I will tell to Professor Durganandani. Okay. So 19th
Okay.
we have you have the MMP2 by Durganandani madam and then AQM by me. Okay. So MMP2 the complex analysis I will see when to take. Okay, I will tell you that. Okay. So I will end the meeting and we'll meet on 20th.